This video is on states of matter and thermal energy transfers. Question 1. Define solid. What are its characteristics? A solid has a fixed shape and volume. Question 2. Define fluid. A fluid is a liquid or gas. Question 3. Define liquid. What are its characteristics? A liquid has no definite shape, but it has a definite volume. Question 4. Define gas. What are its characteristics? A gas has no definite shape and no definite volume. The gas takes the shape of the container. Question 5. Define and give the units for each variable for density rho equals m over v. So density is the total mass of an object divided by its total volume. It's a scalar. So density is given by the Greek letter rho, which is the total mass of an object divided by the total volume of an object, has units of kilograms per meters cubed. Question 6. Determine the volume of a 1 kilogram gold bar if gold has a density of approximately 19,300 kilograms per meters cubed. Let's take the equation rho equals mass over volume and just solve for volume. Question 4. Define diffusion. Diffusion is the movement of particles from higher density to lower density. Diffusion is the spreading out of particles. Diffusion applies to gases. Question 8. Which state of matter has the most potential energy, a solid, a liquid, or a gas? Gases are defined to have zero potential energy. Liquids and solids both have negative potential energy. Gases have more kinetic energy than liquids, and liquids have more kinetic energy than solid. Question 9. Define temperature. Temperature is the average kinetic energy of particles. Question 10. Define degrees Celsius. What is the melting point and boiling point of water in degrees Celsius? Degrees Celsius is a unit of temperature. Melting point is 0 degrees Celsius for water. Boiling point is 100 degrees Celsius for water. Question 11. Define Kelvin. What is the melting point and boiling point of water in Kelvin? Kelvin is a unit of temperature. Has a melting point of 273.15 K and a boiling point of 373.15 K. We don't say degrees Kelvin. We just say Kelvin. So this is important. Delta degrees Celsius is equal to delta Kelvin, because we don't have to take an extra step when doing some problems. Question 12. Define absolute zero. Absolute zero is the minimum temperature possible. At this temperature, the kinetic energy of the atoms are also at a minimum. So in degrees Celsius, it's minus 273.15 degrees Celsius, and Kelvin, it's 0 Kelvin. Question 13. Which has greater kinetic energy, 0 degrees ice or 0 degrees water? Which has greater potential energy? 0 degrees Celsius ice and 0 degrees Celsius water both have the same kinetic energy since they both have the same temperature. 0 degrees water has a greater potential energy than 0 degrees ice. Question 14. Define and give the units for each variable for the equation for Boltzmann's constant. K sub b equals R over NA. Well, this is two constants on the right-hand side have been simplified to only one constant on the left-hand side. So R is the gas constant. We'll learn more about it later, hopefully. And sub A is Avogadro's number. We'll learn more about it later, hopefully. And K sub B is Boltzmann's constant. Question 15. Define and give the units for each variable for the equation for the internal energy of an ideal gas. We'll learn more about an ideal gas later, hopefully. Case sub B is a constant. T is temperature in Kelvin. R is the gas constant. And N sub A is Avogadro's number. Question 16. Define thermal equilibrium. Thermal equilibrium is when two objects have the same temperature. If two objects in thermal equilibrium are touching each other, then there is no transfer of energy or heat between the two objects. Question 17. Define heat. Heat is a transfer of energy between two objects from higher temperature to lower temperature. Question 18. Define internal energy. Internal energy of a system is a total intermolecular potential energy arising from the forces between the molecules plus the total random kinetic energy of the molecules arising from the random motion. Question 19. Define phase change. A phase change is a change in particle behavior arising from a change in energy at constant temperature. Question 20. What does the equation Q equals mc delta T tell us? Define and give the units of each variable. This equation tells us the change in internal energy of the object if its state does not change. So, if we're going to increase the temperature of a solid, we're going to use this equation to tell us how much energy it takes to increase the temperature of that solid. If we're going to decrease the temperature of a solid, then this equation is going to tell us how much energy is going to decrease or taken away from that solid to decrease its temperature. So Q on the left-hand side is a change in internal energy. M is the mass of the object in kilograms. C is the specific heat of the object. And that depends on the properties of the object. And delta T is a change in temperature of the object. So remember, delta Kelvin is equal to delta degrees Celsius. So you don't have to convert to Kelvin if you're given degrees Celsius. Question 21. Define melting. Does an object gain potential energy or lose potential energy when it melts? What about kinetic energy? Melting is when an object changes its state from a solid to a liquid. The object gains potential energy. Kinetic energy stays the same since the temperature is the same. Question 22. Define freezing. Does an object gain potential energy or lose potential energy when it freezes? What about kinetic energy? Freezing is when an object changes its phase from a liquid to a solid, so the object loses potential energy. But kinetic energy stays the same since the temperature is the same. Question 23. Define vaporization or boiling. Does an object gain potential energy or lose potential energy when it vaporizes or boils? What about kinetic energy? Vaporization or boiling is when an object changes its state from a liquid to a gas. The object gains potential energy. The kinetic energy stays the same since the temperature is the same. Question 24. Define condensation. Does an object gain potential energy or lose potential energy when it condenses? What about kinetic energy? Condensation is when an object changes its phase from a gas to a liquid. The object loses potential energy. The kinetic energy stays the same since the temperature is the same. Question 25. What does the equation Q equals mL sub F tell us? This tells us the change in internal energy of the object if its state changes between a solid and liquid. So the temperature of the object remains the same. So this is the meaning of the three variables. Question 26. What does the equation Q equals mL sub V tell us? This equation tells us the change in internal energy of the object if its state changes between a liquid and a gas. The temperature of the object remains the same. And this is the meaning of the three variables. Question 27. Moses has 500 grams of gold. Go online to find the specific heat capacity of gold in its solid state in joules over kilograms times Kelvin. It's 126 joules over kilograms Kelvin. Part B, how much energy will it take to increase the temperature of solid gold by 50 degrees Celsius? So remember this. So Q equals MC delta T. T final is greater than T initial. So our solution is going to be positive. Part C, how much energy will be lost by solid gold if its temperature decreases by 50 degrees Celsius? Well, in this case, temperature initial is greater than temperature final. So delta T is negative. Question 28. How much energy will be needed to increase the temperature of 0.8 kilograms of solid ice from -30 to steam at +140? Draw a temperature versus energy graph of this process. So we're given all of these variables, these values. So to go from -30 degrees water, or H2O, to +140, we need the energy to go from -30 to 0 degrees solid, from 0 degrees to 0 degrees solid to liquid, from 0 degrees to 100 degrees liquid, from 100 degrees liquid to 100 degrees gas, and finally from 100 degrees to 140 degrees gas. So we have these 5 terms here. And we could factor out the mass. And then we could plug in for all of the variables. And then we could simplify it to 3 significant figures. And this is what a temperature versus energy graph looks like. You can see when we increase the temperature of a solid, a liquid, or a gas, the slope is positive. If we change the state from solid to liquid or liquid to gas, the slope is 0. Question 29. Approximately how much energy will be needed to melt 1.25 kilograms of silver, which is at room temperature at 22 degrees Celsius? The specific heat capacity of silver is approximately 236. The latent heat of fusion of silver is approximately 1.05 times 10 to the 5. And the melting point of silver is approximately 962 degrees Celsius. So we're going to use this equation. This first term, MC delta T, is the energy required to increase the temperature of the solid from 22 to 962. And Q equals mL is the energy required to change the state of the silver from solid to liquid. Question 30. Aaron drops a 6 kilogram gold block with a temperature of 20 degrees Celsius into a tub with 2 kilograms of liquid water at 90 degrees Celsius. What will be the final temperature of the system? So the gold is going to get hotter and the water is going to get colder. So the final temperature of the system should be between 20 degrees and 90 degrees. So the change in energy of the whole system should be 0 joules. So the energy gained by gold should be plus the energy lost by water should equal 0. So we have this equation here. MC delta T of the gold plus MC delta T of the water equals 0. Here we're going to plug in what we know. If gold is going to get more hot, then in parentheses it should say T final gold minus 20. If the water is going to get more cold, this should be a negative value. That's why T final water minus 90 degrees is in this order. We know T final gold equals T final water equals T final. So now we only have one unknown. And this is 3 significant figures, our solution. Question 31. A ball of copper which has a specific heat capacity of 390 has a mass of 165 grams and is initially at temperature of 115 degrees Celsius. This ball is quickly inserted into an insulated cup containing 125 milliliters of water at a temperature of 22 degrees Celsius. Part A, what will be the final equilibrium temperature of the ball and the water? Once again, the copper is really hot. The water is really cold compared to the copper. So the copper is going to get colder and the water is going to get hotter until they have the same temperature. So we could convert 125 milliliters to grams. And then we know that the change in energy of the system is 0. So the energy gained by the water plus the energy lost by the copper is 0. So MC delta T of the water plus MC delta T of the copper is 0. So this here should be positive. This is not correct here because the initial temperature of the copper is 115 degrees Celsius. And this here is not correct because the initial temperature of the this is correct for water, M. This is correct for water, C. This is not correct, this last part. This should say T final water minus 22 degrees Celsius. So change this to T final water. This is correct for copper. This is correct for copper, MC. This delta T should say T final copper minus 115. And this should say T final copper equals T final water. And then this is our solution. Part B, how much heat did the copper ball lose to the water? Well, this is mc delta T. Part C, how much heat did the water gain from the ball? This is the solution, mc delta T. Now for parts B and C, they should have the same answer, but because of rounding error from part A, the solutions to part B and C are not equal to each other. Question 32, define conduction, convection, and radiation. Give an example of each. Conduction occurs when energy or heat is transferred by a solid. The molecules are not moving. Convection occurs when energy is transferred by a liquid or gas because of fluid density differences. Here the molecules are moving. Finally, radiation occurs when energy or heat is transferred in a vacuum. We'll learn more about electromagnetic waves when we learn about waves, hopefully. Question 33, what is the difference between a thermal conductor and thermal insulator? Okay. A thermal conductor is an object which transfers heat easily, like metal, and a thermal insulator is an object which does not transfer heat easily, like wood or rubber or plastic. Question 34, describe this equation. So this equation tells us the rate of thermal energy transfer by conduction in terms of the type of material and cross-sectional area of the material and the temperature gradient. So let's just assume T1 is really hot on the left side. How much time does it take for that energy to transfer to T2? Like if T1 is hot and T2 is cold. So K is a thermal conductivity of the material, A is a cross-sectional area of the object, delta T is a temperature difference across the slab, and X is the thickness. Or delta X is the thickness. Delta T over delta X, they call this the temperature gradient. Rate of change of temperature with distance. And delta Q over delta T has units of joules over seconds or watts. Power. Question 35. A silver plate 3 centimeters thick has a cross-sectional area of 4,000 centimeters squared. One face is at 160 degrees Celsius and the other face is at 130 degrees Celsius. How much heat passes through the plate each second? So it's just how much heat passes through the plate each second. That's delta Q over delta T. So we were given K, A, and delta T over delta X. Question 36. A metal plate 6 millimeters thick has a temperature difference of 48 degrees Celsius between its faces. It transmits 200 kilocalories per hour through an area of 7 centimeters squared. Calculate the thermal conductivity of this metal in watts over meters Kelvin. So it says thermal conductivity, so they want us to solve for K. So here we solved for K. And then we also converted kilocalories per hour to joules per second. So this is 1 over area. This here is delta X over delta T. And this here is delta Q over delta T. Where we get this as our solution. question 37. Two metal plates are soldered together. It is known that A equals 70 centimeters squared. L1 is 2 millimeters. L2 is 4 millimeters. T1 is 110 degrees Celsius and T2 is 20 degrees Celsius. For the plate on the left, K1 is 45 watts over meters Kelvin, and for the plate on the right, K2 is 85 watts over meters Kelvin. Determine the temperature of the soldered junction in K and the heat flow rate in joules over seconds. First, determine the temperature of the soldered junction. So, assume an equilibrium condition in which the heat flowing through plate 1 is equal to the heat flowing through plate 2. So we have this condition here. Now remember, T1 is more hot than T2. So T1 is going to get colder, and T2 is going to get hotter. So that's why we have T1 minus T final, and not T final minus T1. And this is why we have T final minus T2, because this is going to be a positive number, this is going to be a positive number. We know A1 is equal to A2. And we're going to get rid of the denominator by multiplying both sides by L1, L2. And now we're going to get rid of the parentheses to get this equation here. And finally, we're going to put T final on one side and T1 and T2 on the other side. And finally, we solve here for T final, which is 339K. Okay, now determine the heat flow rates. So we know this equation here. We're going to plug in all the values to be 6880 joules per second for metal 1. For metal 2, we get 6890 joules per second. So both solutions should have given the same result, but due to rounding errors, they didn't. So just remember how much you should round in the beginning to get the correct answer in the end.